Good morning to those of you here with us in Provence, France. Good afternoon, good evening, and in some cases very early morning to those of you joining us from ITER member countries around the world. My name is 𝗪𝗁 𝗪𝗁, and I am the head of communication here at the ITER project. It is my pleasure to welcome all of you to this first, less formal segment of today's broadcast, in which we will be celebrating the start of machine assembly, a new phase at ITER. We will spend the next hour showing you the ITER Worksite. Then at 11 a.m. France time, we will start the formal ceremony where we will be joined virtually by French President Emmanuel Macron and leaders from the 7 ITER members. Following the ceremony, at about 12:30, we will hold a press conference, part live, part virtual, in which you are also welcome to join us and to view this with us. To kick off the Worksite tour, I now send you to Dr. Bernard Bigot, the ITER Director General, who will give you an overview of the ITER Worksite.
As ITER Organization Director General, I am very pleased to welcome you on the ITER site when we are just starting to celebrate for the new phase for Tokamak assembly. We are around this very nice Provence landscape, and in front of us, indeed, we have what we call the Tokamak building, the Tokamak complex indeed, which is now completed, and behind you have the assembling hall where we are pre-assembling the various components before their installation. We are very pleased that the Tokamak building has been completed and we take over about last March, and now we are ready for assembling all the pieces in, including very recently we have installed the Tokamak masterpiece, which is what we call the cryostat base. On the other side you see the cryogenic plants, which also is very well progressing. You have all the switchyard installation and all the power distribution, and just in front of us it is a converting building where we will convert the AC to DC power. So welcome, and we will visit now more detail of the worksite. Welcome to the Colloidal Field Coil workshop, where the European Domestic Agencies is manufacturing 4 of the 6 horizontal coils we need to have the magnetic cages to be assembled. These coils indeed are made of cable. You have a sample of this cable. The cable is made of superconducting materials. This filament made of titanium niobium. You have inserted them in a jacket because they are fragile. They are in ceramics and they will not be able to sustain the huge magnetic forces. So this jacket is a stainless steel jacket, very heavy indeed, and inside you have a pipe where the liquid helium will flow to cool down this superconducting material at minus 270 degrees in order to have it superconducting and able to transport up to 70,000 ampere of electricity. Let me explain to you, these coils. As I said, we have 6 of these coils. The smallest one are 10-meter diameters and are small enough to be transported. They are manufactured in China in behalf of Europe and in Russia. The largest one, 17 and 24-meter diameters, could not be transported and are manufactured in this workshop. How we will proceed in order to make the huge magnetic cages? We will position the 3 lowest coils in the cryostat, and we will clip the 18 vertical coils. We name them toroidal coil, and we will see some of them very soon, in such a way that we have associated the coil with the vacuum vessel, because the sector of the vacuum vessel will be pre-assembled with the coils. And once we have positioned the 9 vacuum vessel sectors with the 18 toroidal field coils, we will position the 6 upper coils, and we will weld very precisely all together the vacuum vessel sectors in such a way we have a very rigid magnetic cages. The main challenge for ITER is the size, as you see, 24 meter large, nearly 20 meter high, with the precision, because we need to align the magnetic line very precisely. So in this workshop, you could see behind me this frame, the yellow one, which will be indeed the support for the impregnation of the large 24 meter coils. In front of us, we have the 217 coils which are already manufactured. This one is named PF5, and it is completed, just we have to install the connection. And this one is a PF2, where we are still to impregnate the pancake we have piled up when we have winded this cable on the appropriate table. And so now we are able to check, to test these coils, and we do it in the tunnel we have just behind. We will cool them down at minus 90 degrees at the temperature of the nitrogen, and so we will check that the mechanical and electrical properties are according to specification. We could not cool them at the lowest temperature of minus 270 degrees because the cryogenic plant is not yet ready. So let's move now and see the latest coils on site. We just arrived a few weeks ago from China, and so you will have the full collection, the 24, which is on its way to be manufactured, the 17 diameter coils, and very soon the one of 10 meters. So you see, all these tools have been very precisely designed and manufactured in order to be able to manipulate all this various equipment. I'm sure you see the tunnel. We could open the tunnel, position the coils, and make the testing properly. And so, while we are progressing on this long corridor, nearly 250 meters long, we just arrive and look at what is the PF6, the number 6, the smallest coil, just in front of us. We just arrived from China, and we will check it. So here it is, coming from China by boat and unshipped at Marseille Harbor. And you see we have prepared another small tunnel for the checking. And this has been qualified for this mechanical and basic electrical properties, but not yet with the other one, which are at very low temperature, as we explained. So you remember now, 3 types of coils. The largest one still ongoing to be manufactured, which will be ready when we need them in order to be able to assemble the toroidal field coils as well as the vacuum vessel by 2022. And this one, which are already manufactured and ready to be moved in the assembling hall. 24, 17, and 10. And when you see this one, which is already so large, you have difficulty to imagine what will be the 24 one. Very precisely and very rigid, and it will be moved on a trailer entering in the assembling hall we will visit in a few minutes from now. So, if you agree, let's move to the other workshop where we will see the toroidal field coils, which are not manufactured on site. They are small enough to be properly transported and assembled here. Okay, let's move.
model that's been created by Tomasz Szabolek and Martin Wawryk at the Hungarian Center for Energy Research. Thank you both very, very much. Tomorrow we will upload these files onto the ITER public website so that it can be an educational tool for students and teachers from all over the world. You can build this. Yes, you can make your own tokamak in the privacy of your own home if you're a fan, or in the classroom or in your makerspace. And you can follow along with us during ITER assembly phase. Now, your tokamak, like this one, will be a bit smaller than the real thing. This is exactly 1/100th scale. So whereas the ITER tokamak is 30 meters high, 30 meters in diameter, this will be 30 centimeters high, 30 centimeters in diameter. The outer part, what I've removed here so that we can see in, is called the cryostat. This is manufactured in India. It is a giant thermos, a stainless steel chamber that will hold the rest of the tokamak in a vacuum and in a clean and cool environment. Then you have inside, as you can see, this donut-shaped chamber, the plasma chamber called the vacuum vessel. And we have removed 2 segments so that you can see inside. But this will be in 9 of these sectors, each one 40 degrees, to make a 360-degree vacuum vessel chamber. This is where we inject the hydrogen gas, and it is where we heat it until it becomes a plasma, and then fusion energy can occur at 150 million degrees. So how do you contain that? With the magnets. We have 3 magnet systems. These circular ring-shaped magnets are called the poloidal field coils. This is what Dr. 𝗖𝗂 was showing you on the ITER Worksite. So the first of these is among the smallest, the PF5. This was procured by Europe, manufactured in China. This one on top, also quite small, being made in St. Petersburg, Russia. The rest of them are too big to make and ship, so they're being made by Europe right here on the ITER Worksite. And they help to confine the plasma and to pinch it away from the walls. Second system is here in blue. These are the D-shaped or toroidal field magnets, half made in Japan, half made in Europe. There are 18 of these, and together with the 6 PF coils, they will create an invisible magnetic cage that keeps the superheated plasma away from the walls, from the steel walls. The third system, which also helps to create this cage, is the central solenoid, shown here in green and manufactured in the United States. Now, this one will be the most powerful magnet. It's manufactured in 6 coils. In addition to help to create the cage, it makes the magnetic flux lines go in a spiral and then in sort of a twist, and it sends these long sustained pulses through the plasma. So just this week, we actually received the very first of the vacuum vessel segments, sectors from Korea with these port stubs added by Russia. And this means that with the toroidal field coils that have already arrived, we can start to assemble the actual ITER machine. That's why we are celebrating ITER assembly today. So there are, of course, many other pieces, more than 1 million components overall in the tokamak. But I hope that now you have the general understanding of how we use magnetic confinement to create fusion energy in a tokamak, which we hope will power the future. We now return you to Dr. Bernard 𝗖𝗂 on the ITER Worksite. Thank you. If you could help me. Sorry. Yes, yes, please. So, we are now in the toroidal field coil workshop where we are preparing the coils which has been manufactured outside the ITER site by the domestic agencies. Indeed, you have in front of you
two coils, which are the first two ones which will be pre-assembled with the vacuum vessel coming from Korea. They are the number 12 and 13. As you can see, is very detailed shape with a lot of interface with many other components. If you see what is there, you will see the knot, which will allow us to fit the poloidal field coils we have visited a few minutes ago. All this part will be assembled with other components in order to make this coil large magnetic cages, okay, very precisely positioned and able to provide all the very large magnetic field. We could move on, and you could see the way it is made is not exactly the same as the other. The cables are pre-positioned on, okay, a stainless plate, and we will pile, okay, the support, and at the very end, we will put them, as it is with the poloidal field coil, with a polymeric resin. And this package will be positioned in a case. The case is made of stainless steel, and you have to understand, in order to contain the coils and not to break them, you have to position the external surface of the coils package, okay, of the cable package, and the internal surface of the cases with a precision of 0.2 millimeter, while the length of these coils is nearly 20 meters and 9 meters large. Very, very strict challenge, as you could imagine. Myself, I am admiring the capacity of the workers to have made this thing so precisely under the specification of the engineers. It took years in order to demonstrate the feasibility of all these coils, which will be, as the PF coils, cooled down at minus 270 degrees with the liquid helium. So this is the back of the coils, or the upper part of the coils. I would like to show you now the lower parts when it will be vertically dressed. Okay. And you see, you have a huge frame because we don't want to deform the coil. The coil has to be very precisely, okay, maintained in the shape it has. And it's why there is this heavy frame which will prevent any deformation. So now we are entering on the part which is the lower part where you have the electrical connection. So again, you see the amazing shape of these coils with, for example, the part which will sit on the cryostat base in order to be able to precisely, okay, fix every part. And also this casing, which is just embedding the electrical connection. We will need to connect, okay, these coils, 18 of them, to the electrical network, and with an intensity of 70,000 amperes at a temperature of minus 270 degrees. And now we are preparing the last checking in order to be sure that there is no leak in the piping delivering the liquid helium. It is on site. After the traveling, we are able to do that and to well prepare this coil in such a way they will move to the assembling hall and be dressed up and assembled, as I will explain in a few minutes, in the assembling hall with the vacuum vessel sectors. For me, it's really impressive to see the quality of the work. And for example, when I see this shape here, the complexity and all is according to the strictest specification. So let's move now to the next steps where we will see the cryostat. The cryostat base is already in the pit, but we need now to position what we call the lower cylinder and upper cylinder to assemble them together. So now we are on the work site, crossing by the upper cylinder of the cryostat. It is 30-meter diameter, nearly 10-meter high, and it has been cocooned in order to maintain a controlled humidity and temperature. It comes from India, and it has been pre-assembled on the work site in the workshop we are now visiting. We pass by near the assembling hall, the cleaning facility building, as well as a radio frequency heating system. Okay, all these pieces are necessary in order to ensure that we will have full control of the hot plasma we are now preparing. So, really amazing to see this large cocooned, lower cylinder and upper cylinder. Indeed, we have opened the cocooning very recently because we want to start the assembling, and we need this lower cylinder to be positioned in the Tokamak pit. So we just now arrived to the workshop where we have been able to manufacture the cryostat component. Indeed, it comes in 54 pieces, but each of them weighing of the order of 100 tons, and the size could be of the order of 10 meters. And now they have been assembled in 4 main pieces. The 4 main pieces is a base, like a can, when you have a bottom of the can, and you have 2 cylinders. You will put one over the other. You will weld with the base, weld between these 2 cylinders, and after that, you have a cover, a top lid. As you see in front of you, you have the lower cylinder. So it's a huge stainless steel part with a lot of opening. All this opening is in order to allow some robots to come in the vacuum vessel, as well as the cool water and the hot water we will extract, and also many diagnostics. This cylinder is 30-meter diameters, and we will have to fit the 2 pieces, 30-meter diameter above the other 30-meter diameters, with a precision of ½ centimeter. The thickness of the stainless wall is 6 centimeters, and it has to be leak-proof. All the welding has to demonstrate that it will not leak even with a very high vacuum. So I propose that you enter within the internal part, where you will see the size of the cylinder altogether, as well as all the very precise penetration. This penetration has been fit together in such a way they are fully aligned with the 2 other parts. One, it is the vacuum vessel, and the other part is the bioshield wall you will visit quite soon. So very high precision and very tight element has to be assembled in such a way that you confine completely, okay, the different parts now. So I guess you understand the challenge, and India, as well as some European companies, has made a wonderful job in such a way that everything is according to specification, without any deviation so far. So the size of the port, as I explained, is appropriate, and in order to have a robot coming in, for example, in order, for example, to position the tiles which will be covering the wall of the vacuum vessel. Now I propose to you to move and to enter into the cleaning, okay, facility building. Okay, so we have to go around. So you see, we open the big door, a trailer will come, okay, and transport the lower cylinder. The mass is of the order of 400 tons before entering in the cleaning, okay, facility building. It's like a buffer. In this cleaning room, indeed, you will check that it is clean and that there is no dust. All specifications are according to the need of the project. And before we go to the next step, which is to move them in the assembling hall. So this big door will open, and it will allow to have the big poloidal fill coil just behind us where we have visited, the toroidal poloidal fill coils, which are the one visited coming from Japan and Italy, and this large vacuum vessel sector and cryostat parts. So let's enter. So we are now in the cleaning facility. You see the soil is very clean. Electronic workshop, because we don't want any dust, any small material which could not be compatible with the functioning of the Tokamak. So you see the size of the gantry crane, able to move the different pieces. And we are moving on in order to enter into the assembling hall, where we will pre-assemble the piece and also to be able to lift them above the ground, more than 30 meters high, to pass over the Tokamak wall and position the component precisely in the Tokamak pit, in what we call the bioshield wall, this huge concrete cylinder, made of large concrete, and to prevent any leak of the neutrons. So let's move. As you understand, these various pieces has to be assembled with a very high precision, is why this assembling hall need to be temperature controlled. The temperature which will be 19 degrees plus or minus 0.1 degrees, in order to avoid any dilatation or contraction of the various pieces from one time to the other one. This huge assembling hall, 100 meters long, 60 meters high, 60 meters large, is needed to accommodate the various pieces. The main points is this huge crane just above us. Each of them could move up 750 tons, and we could couple both of them in order to be able to lift up to 1,500 tons with a precision of millimeter. And very recently, we have been able to move the cryostat bays and position them within the bioshield wall, the Tokamak pit, with a precision of millimeter, according to specification. So we are moving on, and we will celebrate in a few minutes the assembling events, and we will be very pleased to listen to the various dignitaries of the ITER members about their perception of the ITER project. So I would like, before we go further, to show you something which is quite spectacular. They are what we call the assembling line. The critical piece of the process is to assemble, as I explained to you, the vacuum vessel sectors, 9 of them, with the thermal shield, because we need to protect the coils from the hot temperature of the vacuum vessel, and the toroidal field coils. We have to assemble 2 coils with 1 vacuum vessel and the thermal shield which is appropriate. And for that, we have designed what we call assembling line. There are 2 assembling lines because it will take between 4 to 6 months to assemble one of these vacuum vessel sectors and the coils, and we could not afford to multiply 6 by 9, which will be 54 months, which will not be compatible with our schedule. So we have 2 assembling lines. These tools have been manufactured in Korea, assembled in Europe. The principle is quite simple. Think about a book, okay? And you make 3 packages of pages of the book, okay? On the central package, you will fix the vacuum vessel sectors. On the lateral package, you will fix the coils, 360 tons, as we saw a few minutes ago. And you will move the pages, to close the angle, and with jacks, and you have jacks, you will adjust the positioning in the space of the coils, and you will pass the coil to the vacuum sector like a ring to the finger of a lady. The ring is 360 tons, and it has to be positioned with a very high precision. It's amazing, you see all the jacks able to position the coils in any direction as needed. And to position the coils and the vacuum vessel sectors, we need to have some special tools. One of these is this very large cradle, where you will install in the vacuum vessel sector, 450 tons, and you will lift up and position in very precise position, in the assembling line. You see, it is on this support that you will have, the vacuum vessel sector position and the 2 panels able to be closed. This is over 25 meters high, and when it will be pre-assembled with the crane, you will lift the whole package and move over the Tokamak wall just in front of us in order to be able to position in the Tokamak pit. And you see this part, for example, are mock-up made of concrete in order to check and train the operators in his capacity to pre-assemble the different pieces I just mentioned about. Now let's enter into the Tokamak. As I explained, the Tokamak has to be very clean. Is why, even if it is a work site, we are protecting the pieces with some special corridors. Thank you. And so we are moving in front of what we call the Tokamak pit with the bioshield wall. We just arrived. It is precisely here where we will have the plasma, 150 million degrees, okay, burning. So it is the famous bioshield wall made of concrete with all the opening which will be fitting with the opening in the cryostat and fitting with the opening in the vacuum vessel. You see it? It is now completed. And so all the pieces will come from the roof because they are so large we could not accommodate to them to introduce them through the doors. You see already positioned, okay, at the bottom of the Tokamak pit, the cryostat base. It is a piece which has been positioned by the end of May, and we have been successful to position them with a precision below 3 millimeters on any parts, okay, of the cryostat base with the support. High precision and very high quality. So you will see on the cryostat base this hole, which are already drilled, where you will position the foot of the toroidal field coil we saw a few minutes ago. So 18 of them will be positioned supporting the vacuum vessel with previously the positioning of the poloidal field coils. And you will see at the bottom, we have these holes, which are what we call the feeder, okay, which will be the line in order to feed the coils with the 70,000 ampere I was speaking about. So let's imagine by end of 2025, when we will have pre-assembled and assembled all the components, made the checking and testing of the vacuum vessel capacity and the coils, okay, magnetic field, we will start to have a first plasma. After that, we will need to complement this facility with the equipment needed to collect, okay, the energy, the famous neutron and helium, and we will offer by early 2029 the first possibility to the physicist to play with the machine and have a real physics experiment. It will not be the full fusion power because we still would need some extra heating, but it will be really a major step ahead. And after that, some extra heating will be installed, and finally, the recycling plant in order to recycle the fuels, because, as I explained already, in the vacuum vessel, you will have only 2 grams of fuels. 1% of these 2 grams will fuse, producing a lot of power, 500 megawatt of heating, while you feed in only 50 megawatt. So the yield is 10 times larger. And so when you will have this fusion, you need to extract the helium and to recycle, okay, the fuel. So once all these various components will be installed, we will be ready for full fusion power, and the schedule is by, okay, end of 2035. It could seem long for you, but you can imagine how precisely we have to manufacture each of the large components, never been done before. It is really a first of a kind, and quality has to be at the highest level. So I guess we could leave on, okay, the workers going on. We have a very strict schedule, is why we don't stop the work today, okay, just to be sure that we are all aligned on our schedule. Okay, so I propose to you we move back and we prepare for the ceremony. Django, are you?
I hope that our worksite tour has given you a sense of the scale and complexity of the ITER project. We will soon be starting the formal ceremony portion where we will hear from each of ITER's 7 members. Now you notice that at times we talk about 7 members or 35 countries. That is because Europe's membership is actually held through Euratom. That means that Europe represents both the work of the 27 countries of the European Union plus Switzerland plus the United Kingdom. Each of the 7 members holds a seat on our oversight body, the ITER Council. Today we will hear from the leaders of each member as well as from the ITER Council Chair. I mentioned earlier that the Tokamak will be made up of more than 1 million components, and if you take individual comparts, more than 10 million parts. These components are designed and fabricated in factories, laboratories, universities all over the world. When they arrive here, they will all need to fit together and they will need to be on time and according to our rigorous schedule. This is what adds complexity to the ITER project. But of course, it also adds a great value. The collaboration of all of these countries, each with unique expertise contributing to a single machine, to a single goal. Let me point out one more contributor. ITER's parts are created in general by scientists and engineers. But one part, a bolt, just like the one I am holding here, was fabricated by an artist in New York, Christine Corday. Ms. Corday was inspired by the ITER project and proposed to contribute. She forged this 10-centimeter bolt and another one exactly like it, manufactured to the same precise material specification as the 40,000 other bolts that were inserted into the steel roof anchors of the Tokamak building. This one inserted by Director General Bernard Bigot himself. Ms. Corday calls this work of art sans titre, or untitled, as a way of expressing how art and science often anonymously drive each other to create the best of our human dreams and aspirations. This bolt will be constantly watching over the plasma from where we placed her as a silent witness of the work of so many scientists, engineers, and workers to make ITER a success. You can read about this and hundreds of other stories that are unique to the ITER project on our public website, www.iter.org. We are now coming to the end of our Worksite tour. I will leave you with a few images from our most recent drone videos as we prepare to start our formal celebration with President Emmanuel Macron and leaders from around the world starting at 11 a.m. France time. Good morning and welcome to all of you who are just now joining our broadcast of the ITER Start of Assembly ceremony. We have just concluded the Worksite tour and are beginning to start the formal ceremony. For that purpose, I would like to turn to the man who has been leading this project with remarkable intensity and dedication for the past 5 years and a little more. Please welcome Dr. Bernard Bigot, the ITER Director General.
Thank you very much, 𝗪𝗂. Welcome to all of you who are joining us. Those who are physically present here with me in the ITER Assembly Hall. Those of you with me here on the stage, representing the 7 ITER members, and those of you joining us virtually from all around the world. Above all, on behalf of the global ITER community, let me express my thanks to the President of France and the other heads of state and ministers representing ITER members who are joining this celebration remotely. We together, with the ITER Council Chair, Monsieur Luo de Lange, are deeply honored by your presence and participation. It illustrates the importance of what we are celebrating, the start of machine assembly at ITER. Today is an historical moment. Fusion energy is a gift of God's. It is because of hydrogen fusion that we are all alive today. Without fusion taking place in the sun, we would not have no light or warmth. This would be no life on Earth. The concept of recreating that incredible energy sources here on Earth is a typical human approach to take the best of nature. We try to understand nature, and then we try, with human imagination, to recreate what nature shows us. But nothing is typical about the ITER project. It is a first-of-a-kind machine, made up of many first-of-a-kind components and breakthrough invention. To build this machine, a star on Earth requires a level of international collaboration that is also first-of-a-kind. When I think about the significance of this point in ITER history as we launch machine assembly phase, 3 points come to my mind. First, we feel the weight of history. It is now 100 years ago since scientists first understood that fusion energy was a power source for the sun and stars. It is more than 60 years since the first Tokamak was built in Soviet Union. In that context, when we consider we have a little more than 5 years to go before ITER's first plasma, it does not seem so long. Whatever we accomplish here at ITER, clearly we are building on the scientific discovery and technological innovation of decades of researchers and inventors. We could not be here if we were not standing on their shoulders. Let us thank them and pay tribute to their works and wisdom. This machine will offer to their successors a unique opportunity to understand for the first time the behavior of an ultra-hot, ultra-low density burning plasma they have been dreaming about. Second, we feel the need for both urgency and patience. We know we need a replacement for fossil fuels as soon as possible. We understand very clearly the promise of fusion power as a safe, reliable, environmentally sustainable, and virtually unlimited source of energy. If fusion power becomes universal in complement to renewable energies, the use of electricity could be expanded greatly to reduce the greenhouse gas emissions from transportation, building, and industry, enabling
the exclusive use of clean energy will be a miracle for our planet. But building a fusion power plant is not easy. We are moving forward as rapidly as possible, but in order to succeed, we must also be deliberate. Quality and safety have always to be first. If we succeed, it will be worth all the time and efforts that have brought us to this point. Thirdly, we feel a deep sense of gratitude for the enduring support of ITER members. We are grateful to the government that provides us with funding and direction. We are grateful to the 10,000 workers at every level in every ITER member countries. We are committed to making ITER succeed. We could not do this alone. With your help, we have completed about 70% of the total construction work leading to first plasma. Today, as we look forward to the machine assembly phase, we know that the hardest part lies ahead. Constructing the machine piece by piece will be like assembling a giant three-dimensional puzzle on an intricate timeline. Every aspect of project management, system engineering, risk management and logistics of the machine assembly must perform together with the precision of a Swiss watch. We have a complicated script to follow over the next few years, definitively. We understand the need of humanity for clean energy. Our goal is to leave a better energy future for our children and future generations. So we move forward with a deep sense of purpose, with gratitude for this historic opportunity. We cannot afford to fail. It is now my pleasure to introduce Monsieur Luo Delong. Monsieur Delong has been one of the leaders of the ITER project for many years, leading the Chinese domestic agencies, as well as representing China in the ITER Council. He is the current chair of the ITER Council. I give the floor to Monsieur Luo Delong.
Thank you, Director General Bigot. Good morning to everybody. On behalf of all the members of ITER Council, I would like to repeat and echo the sincere welcome you have already extended to all our guests. I would especially welcome, with a deep sense of humility, our host, President Macron of French Republic, President Xi Jinping of the People's Republic of China, my own country, and the other heads of state and senior ministers, extending congratulations to this celebration. Your presence, in one way or the other, is a testimony to the historic importance of this occasion. I'm really sorry not to be able to be there in person, but it's a privilege to participate in this remarkable event. The COVID-19 pandemic has made all of us learn to operate differently, often at a distance. Last month, the ITER Council met virtually for the first time in its history. Being at a distance, however, has not made us care any less about the ITER project, nor has it reduced our sense of pride and sometimes amazement. As we see the outstanding progress that has been made over the past 6 months, with the pandemic impacting so many aspects of our lives. This challenging time has coincided with a critical period in the ITER schedule. I'm referring to the completion, transport, and arrival at the ITER site of the most important first-of-a-kind components. Some of these components have been worked on for over 5 years, or even more than 10 years. They weigh hundreds of tons, requiring special shipping conditions across oceans, over special railways, and using unique vehicles. When the pandemic hit, the ITER Council watched with pride as the ITER community came together to develop a prioritized continuity plan. That plan has been carried out with precision in every detail. As with countries around the world, France has suffered during this pandemic. And yet, remarkably, there has not been a single COVID-19 infection on the ITER Worksite. It is what Director General Bernard Bigot has come to call the ITER miracle. On behalf of the ITER Council, I congratulate Dr. Bigot for his unwavering leadership during this difficult period. And I salute the entire ITER community, every member, every domestic agency, every supplier company or contractor, and every staff member for their dedication, perseverance, commitment, and hard work. If we are able to continue in this way through the machine assembly phase on which we embark today, I have great confidence that we will succeed. Thank you.
Thank you very much, Chairman 𝗖𝗂. Your support is highly appreciated. Today is a very special day for ITER and for all ITER members. After many years of preparation and a lot of efforts everywhere in the world, we are ready to celebrate the start of the Tokamak assembly phase. Indeed, we are now able to launch this new phase in parallel with the design and manufacturing phases because we have received recently, as planned 5 years ago, all the first components from the ITER members we needed to proceed. The Tokamak building and the assembling hall from Europe, the 3 large pre-assembled parts of the cryostat from India, the first sectors of the vacuum vessel from Korea with parts from India and Russia, the thermal shield from Korea, and the 2 first toroidal field coil from Japan. Furthermore, the many other components that will complement this first step are all on their way to be delivered through 2022, including the feeders from China and the central solenoid from the US. In 2006, in Paris, the 7 ITER members decided to locate the project in Europe, more precisely in Provence, France. Since then, France, as the host state, has provided the best support to ITER and has fully complied with its commitment. It is highly appreciated by all ITER members. During the last 3 years, President Macron has always been very supportive of ITER and helpful to overcome any major difficulty we may face. We are very grateful for your always timely and decision action when ITER calls upon you, President Macron, to help, including for your participation today. So it is my large and sincere pleasure and honor to give you the floor, Mr. President, from Élysée Palace in Paris, which is precisely where the ITER agreement was signed 14 years ago on 21 November 2006. Mr. President, we are listening to your introductory speech before we listen to the high dignitaries from all of the ITER members, and we would like to warmly thank them as well for their participation and continued strong support.
Il est des moments où les peuples, les pays du monde choisissent de dépasser leurs différences pour se hisser à la hauteur de l'histoire. Et le lancement, au milieu des années 2000, du projet ITER est de cela. ITER, c'est une promesse de paix. Les États-Unis, la Russie, la Chine, le Japon, l'Europe, l'Inde et la Corée mettant à disposition leurs plus grands scientifiques, leur meilleur savoir-faire pour le bien commun. C'est la preuve que ce qui rassemble les hommes et les États est plus fort que ce qui les divise. ITER, c'est une promesse de progrès, de confiance dans la science. Et c'est d'ores et déjà une prouesse scientifique et technologique. Imaginez que l'expérience soit concluante, qu'elle puisse trouver demain des applications industrielles. Nous aurons mis au point là une énergie non polluante, décarbonée, sûre et pratiquement sans déchets, qui permettra tout à la fois de répondre aux besoins de toutes les zones du globe, de relever le défi climatique et de préserver les ressources naturelles. Avec la fusion, le nucléaire peut être une filière d'avenir, encore plus qu'il ne l'est déjà. ITER, c'est précisément un acte de confiance en l'avenir. Les plus grandes avancées de l'histoire ont toujours été des paris, des parcours semés d'embûches. Au départ, on pense toujours que les obstacles seront plus forts que la volonté de faire, d'avancer, et ITER renoue avec cet esprit de découverte, d'ambition. Avec cette idée que grâce à la science, demain, en effet, peut être meilleur qu'hier. C'est pourquoi je suis fier que notre pays accueille ce projet pour l'avenir de l'humanité. ITER en latin signifie le chemin. La France, dans une Europe forte, entend à nouveau être de ces forces qui tracent pour le monde un nouveau chemin, un chemin de prospérité, un chemin de progrès pour tous. Merci à vous.
Clearly, we owe a big thank you to President Macron. We are now going to turn to a short video for you, which will recall the contributions of the 7 ITER members that is making this transition possible at ITER, and it will explain a bit about machine assembly.
ITER, the world's largest tokamak, will demonstrate the scientific and technical feasibility of fusion power. 30 meters in diameter and nearly as many in height, the ITER tokamak is a marvel of engineering, created from an estimated 1 million components. The size and weight of the major components, the tiny tolerances for the assembly of major systems, the diversity of manufacturers, the tight schedule, all of these elements combine to make ITER an engineering and logistics challenge of enormous proportions. It was in November 2006 when the 7 ITER partners gave the starting signal for one of the largest international scientific endeavors ever attempted. Soon after, diggers and scrapers moved in to prepare the 180-hectare stage. And here we are today, 14 years into realization, celebrating the official start of machine assembly. Despite the challenges of the COVID-19 pandemic, we have managed to maintain critical activities on the worksite, including the reception of a number of ITER's exceptional first-of-a-kind components. In March, the European domestic agency, Fusion for Energy, put the finishing touches on ITER's assembly theatre. A vast hall for preparing, then installing machine components. In April, the first 2 toroidal field coils, superconducting magnets weighing 360 tons each, arrived from Italy and Japan. In May, the 1,250-ton cryostat base, supplied by India, was successfully positioned in the Tokamak pit. Late June, the first ring-shaped poloidal field coil procured by Europe arrived from its manufacturing site in Hefei, China. Russia and the United States are also progressing in the procurement of critical path components for ITER. Finally, the first sector of the ITER vacuum vessel shipped by South Korea has arrived on French soil and will soon be transported along the ITER itinerary to the worksite. The buildings and infrastructure needed for first plasma are 75% complete, and the pace on planet ITER is picking up as machine and plant components arrive from the 7 ITER members. The time has come to put the world's largest puzzle together, the assembly of the ITER machine. Following the spectacular lowering of the cryostat base, the further assembly of the ITER Tokamak will proceed in a bottom-up fashion. Machine installation will continue with the lower cryostat components, the lower thermal shields, and the temporary support structures for colloidal field coil number 6. A set of spare pre-compression rings are the next in line, followed by the central support structure and the 18 gravity supports for ITER's huge toroidal field coils. Thermal shields that will help protect the superconducting coils are attached, and finally, colloidal field coil number 6 is lowered into the pit, followed by colloidal field coil number 5. In order to prepare for the arrival of the pre-assembled vessel sectors, an inner support column, a work floor, and 7 radial beams are put in place to stabilize the structure during assembly and welding. While the lower cryostat components are being assembled and welded in the Tokamak pit, 2 giants are standing in wait in the adjacent assembly hall. Standing 6 stories high, the purpose-built sub-assembly tools will suspend each of the 9 sectors of the vacuum vessel in turn, while thermal shield panels and toroidal field coils are rotated into position. By the end of this year, the first completed sub-assembly will be transferred to the Tokamak pit. 8 others will follow. Last in line is the 18-meter tall central solenoid. The powerful electromagnet will be the last major component to be installed in the machine pit before the cryostat is closed up. In all, dozens of custom tools will be required to assemble, lift, and finally maneuver ITER's super-sized components. The tools will have a range of lift capacities: 500 tons for the upending tool that will turn vacuum vessel components from horizontal to vertical, and 1,500 tons for the heavy lift cranes that will carry all major Tokamak components into the Tokamak pit for assembly and welding. The precise alignment of ITER's largest and heaviest components to within tolerances of 2 to 3 millimeters is essential to the successful operation of the machine. Assembly sequences have been planned with this in mind and will utilize sophisticated optical metrology techniques at each step of the assembly process. The closure of the cryostat by late 2024 will mark the end of the first assembly phase. The ITER machine will undergo 1 year of integrated commissioning and testing, culminating in first plasma at the end of 2025. Beyond its symbolic importance, ITER's first plasma will be an important trial run for the machine, a first occasion to verify the correct alignment of the machine's magnetic fields and the correct functioning of key systems. The very first low-power hydrogen plasma, lasting only a few milliseconds, will be followed by other shots of increasing power and duration. This shakedown mode, lasting a few months, will be followed by a shutdown phase, during which key systems for hydrogen and helium plasmas at nominal power are installed inside the vessel, such as the blanket, the diverter, and in-vessel coils. These components will be introduced through dedicated port cells in the vacuum vessel, requiring a whole host of custom-made tools, work platforms, and cranes. The world will be watching as decades of planning come to fruition, and the ITER Tokamak is assembled from components shipped from all around the world by the 7 ITER members. ITER, leading the way toward
Thank you very much to the ITER assembly team that helped us a great deal in getting that video exactly right. We now turn to the global tour, where we will hear from each of the 7 ITER members. First, speaking on behalf of the host member, European Commission President Ursula von der Leyen was hoping to be with us today, but unfortunately was unable to do so due to unforeseen circumstances. Therefore, speaking for the European Union, we will turn first to Michael Meister, the State Parliamentary Secretary for Germany, and he will be speaking on behalf of Chancellor Angela Merkel for Germany's presidency of the Council of the European Union.
Director General 𝗖𝗁, Your Excellencies, esteemed staff of the ITER organization, distinguished guests. It's a great pleasure to speak to you today as a representative of the Federal Republic of Germany. May I convey warmest regards and well wishes from Federal Chancellor Merkel and from Federal Research Minister 𝗪𝗁𝗁. It is a pity that I'm unable to attend today in person and have a look to the progress made at the ITER building site. But the pictures and the videos that I have seen on the ITER website are clear proof of the amazing progress made. Buildings and facilities, which were still in the very early stage of construction during my visit at the beginning of the last year, have since developed into splendid structures. This is particularly true of the Tokamak complex. A year ago, I guessed into the huge pit where the machine was to be built. The recent installation of the heaviest component of the ITER, the 1,250-ton base section of the cryostat, and now the assembly of the Tokamak means one huge piece of the puzzle will be followed by the next. It marks the start of assembly of the ITER machine. The ITER project has reached a critical milestone, and this is an occasion which deserves to be celebrated. Please allow me to take this opportunity to congratulate the entire team of the ITER organization and you, Mr. 𝗖𝗁, in particular, for this latest achievement in the construction of ITER. The ITER project involves 7 partners. Besides the European Union, they are China, India, Japan, Russia, South Korea, and the United States. This fact makes one thing clear. Without the contributions made by each individual ITER partner, we would not have reached the milestone we are celebrating today. And that is why my congratulations also go to all the ITER partners. I am well aware that the entire team of the ITER organization is facing enormous challenges due to the COVID-19 pandemic. Work steps planned have to be rethought. Staff absence have to be compensated. Restrictions on imports and specific circumstances of the respective ITER members are complicating the timely delivery of components. The fact that the construction work is continuing despite these hurdles and that measures to minimize risks are being carried out at full speed shows that the project is in good hands. We are living in an age in which the search for alternative, sustainable sources of energy is of vital importance for the global climate. Solar energy and wind power are sources which we have already tapped with success. The increasing demand for energy worldwide means we must investigate a broad range of options to secure future energy supply. Fusion research makes a contribution to long-term application-oriented basic research. Fusion is a focus of Germany energy research. The outstanding scientific know-how available in fusion research puts a global responsibility on Germany to advance the understanding of fusion processes for energy generation purposes. This is why Germany is supporting the completion of ITER according to the planned time and cost schedule. Germany will also continue to secure adequate funding for the ITER project during its EU Council presidency. Because ITER is an international project, it poses challenges which we can only solve by taking action together. After the stage win, which we are celebrating today, we are very much looking forward to the next big milestone, the first plasma. Until then, we will continue to cooperate with Fusion for Energy to ensure that the European in-kind contributions are made on time and that our financial obligations are met. I wish the entire team of ITER organization all the best and great success. And above all, please stay healthy.
Thank you very much to State Secretary Meister as well as to Chancellor Merkel. We now give the floor to the European Commissioner for Energy, Kadri Simpson.
Presidents, Prime Ministers, Ministers, Director General, distinguished guests, greetings. I'm very happy to be speaking to you all from Brussels. I'm sorry I cannot be there in person today, but I'm looking forward to visiting the site as soon as possible and seeing your great achievement firsthand. Today, we mark an important milestone for the ITER project and for fusion energy development. 10 years of work and 10 million components will culminate in the world's largest fusion research device. We cannot understate the importance of this as a technical achievement. Almost every individual element of ITER is at the cutting edge of its field. And I'm looking forward to seeing these extraordinary components combined to make something even greater than the sum of its parts. But today we celebrate more than just a technical milestone. I would like to highlight 3 things in particular. First, the strength of international collaboration. This work has benefited from the global collaboration between the ITER members. And I want to thank our partners from China, India, Japan, Korea, Russia, and the United States for making this journey with the European Union. Without your participation and contribution, we would not be here today. I would also like to thank the European Domestic Agency and Fusion for Energy, as well as all the European companies and research organizations. Each of you have worked tirelessly to deliver the European contribution to the ITER project. Reaching today's milestone would not have been possible without all parties working towards a common goal. Second, ITER represents the determination of the EU in the fight against climate change. This Commission has adopted the European Green Deal as its roadmap to climate neutrality by 2050. In that light, the clean energy transition is both an ethical necessity and an economic opportunity. ITER perfectly demonstrates this duality. It is a major investment in our high-tech industries and clean energy sources for the future. Finally, I would like to talk about the importance of continuing to support projects like these in challenging times. The COVID-19 pandemic has forced us all to readjust our priorities. Europe is no exception. The European Commission has revised its proposal for its long-term budget and proposed the next generation EU to tackle our recovery. The journey might change, but our end goal remains the same, and so our commitment to projects like ITER cannot waver. It is not only a milestone on the path to fusion power, but also a valuable tool for investment and development of our industries. This is why the European Union will maintain its support to ITER over the next 7 years. To finish, I want to thank all of you for your strong willingness to make a success of ITER, and what a success it has become. I also want to give special thanks to the representative of industry and the research community assembled. We have learned so much from you. You are the beating heart of ITER, and its success depends on your vision, creativity, and hard work. Of course, challenges still lie ahead of us. From this point on, our work becomes even more delicate and complex. But month after month, as a result of your work, plans are becoming reality, and fusion research will soon lead to fusion energy. We are on the right track, so let's celebrate our successes while looking forward to those to come. Thank you and enjoy today's event.
Thank you, Commissioner Simpson. We will now hear statements from each of the other 6 ITER members presented according to our custom in alphabetical order. So first, for China, we will hear a statement by President Xi Jinping, the President of the People's Republic of China, read on his behalf by the Minister of Science and Technology, Wang Zhigang.
尊敬的马克龙总统，尊敬的比格总干事，女士们、先生们，我是中国科技部部长王志刚，非常高兴出席伊特计划重大工程安装启动仪式。今天是伊特计划重大工程安装正式启动的重要时刻，也是该计划进程中具有里程碑意义的活动。中国政府对伊特计划高度重视，习近平主席专门发来贺信。下面，我荣幸地向大家宣读中国国家主席习近平致伊特计划重大工程安装启动仪式的贺信。贺信值此国际热核聚变试验堆计划重大工程安装启动之际，我谨表示热烈的祝贺。科学无国界，创新无止境，国际科技合作对于应对人类面临的全球性挑战具有重要意义。国际热核聚变试验堆计划承载着人类和平利用核聚变能的美好愿望，是当今世界最重要的国际科研合作项目之一。国际热核聚变试验堆计划实施以来，中方始终恪守国际承诺。中国企业和科研人员勇挑重担，与国际同行齐心协力，为计划的顺利推进贡献了中国智慧和中国力量。10多年来的积极探索和实践，充分证明，开放交流是探索科学前沿的关键路径。当前，全球正面临新冠肺炎疫情带来的严峻挑战，人类比以往任何时候都更需要携手前行，共克时艰。中方愿继续同各方加强科研交流合作，合力突破重大关键科学和技术，推进全球科技创新，为增进各国人民福祉，实现全球可持续发展不断做出新贡献。中华人民共和国主席习近平2020年7月28日宣读完毕。
Thank you so much, Minister Wang, and of course we are deeply honored for having the statement by President Xi. Please now give your attention to Mr. Jawed Ashraf, the Indian ambassador to France and Monaco, who will present a statement from the Prime Minister of the Republic of India, Narendra Modi. Thank you.
It is my honor and privilege to deliver a message on behalf of Prime Minister of India, Shri Narendra Modi. The Director General of ITER, members of ITER, distinguished members of the scientific community of many nations, ladies and gentlemen, Namaskar. My warm greetings to you on this historic occasion. Today we are celebrating the beginning of the ITER assembly activities. It is an important milestone in the progress of the ITER project. We have reached it after an extraordinary journey of many years of commitment, dedication, and hard work by scientists, engineers, and technicians. They have successfully developed and fabricated a wide range of entirely new components that represent design, innovation, and engineering of great complexity and precision. They have done this while adhering to schedules and timelines. Indeed, the ITER organization deserves special appreciation for maintaining its schedule of activities in recent months, despite the disruptions and restrictions of the ongoing pandemic. India is proud to be part of a global enterprise that is at the frontier of science and engineering. Indian scientists have made valuable contribution to the development and fabrication of the cryostat, the cooling system, the cryo distribution system, and several kilometers of cryolines. They remain involved in many other aspects of the project. They have demonstrated India's capabilities for design and manufacture at the most advanced levels. Equally, our institutions, scientists, and engineers have benefited enormously from collaborating with their peers from around the world. ITER is a project of an extraordinary vision and ambition, and of unparalleled scale and complexity. By seeking to simulate the sun's energy production on Earth, it is attempting a task of cosmic proportions. It is as much a testimony of a relentless human pursuit of knowledge as it is of our enduring quest to use science for the welfare of humanity. In this case, as an abundant, clean, and sustainable source of energy. The project is also very special because it involves international collaboration at an unprecedented level. This shared endeavor for our common good is a perfect symbol of the age-old Indian belief, 𝗖𝗎 𝗪𝗁𝗁. That means the entire world is one family. Today's event is an important step towards a better tomorrow for mankind. And on behalf of 1.3 billion Indians, I wish the ITER project all success. Thank you.
Thank you, Ambassador Ashraf, and of course, Prime Minister Modi. Now we will give the floor to 𝗖𝗎 𝗪𝗁, the Japanese Minister of Education, Culture, Sports, Science, and Technology, who will present a statement by the Prime Minister of Japan, Shinzo Abe.
おはようございます。日本国の文部科学大臣の萩生田光一です。核融合エネルギーの実現に向けた国際プロジェクトであるITER計画における重要な工程である実験炉の組み立て・据え付けを開始するとのこと。1980年代後半から深く関与してきた日本として大変喜ばしくお祝い申し上げます。核融合エネルギーは日本政府が策定した革新的環境イノベーション戦略において脱炭素社会を実現するための革新的技術の一つとして位置づけられており、私としても強力にその推進を図っているところです。折しも全世界で新型コロナウイルスが猛威を振るっている中、ITER計画において日本が製作した世界最大級の超電導コイルがITERサイトに納入されるなど、目標スケジュール通り実験炉の組み立て・据え付けを開始することができました。これは美後機構長がおっしゃるITERミラクルであり、我々の強靭な意志と連携・実行力の賜物と考えます。このように建設・機器製作活動をさまざまな工夫をしながら推進をしていただいているITER機構や各局の研究機関の取り組みを称賛したいと思います。日本においてはITER計画とともに日欧が開始した BA 活動のもと、3月末に核融合実験装置 JT60SA の組み立てが完了したところです。これらの研究開発による成果によって日々の生活をより豊かにすることを祈念しつつ、 ITER 計画の連携をさらに強めていきたいと考えています。ここで安倍首相の祝福メッセージをいただいておりますので、代読をさせていただきます。この度、日欧米ロ中韓印の協力により、フランスにて建設が進んでいるITER 計画が実験炉の組み立て据え付け開始という新たなステージに入ることに心から祝意を表します。気候変動という地球規模課題に立ち向かい、脱炭素社会を実現するには革新的なイノベーションの創出が必要です。日本は核融合エネルギーの実現に向け、本計画の黎明期から関与してきました。新型コロナウイルス感染症の世界的な広がりの中にあっても、強固な国際的連帯により、引き続き本計画が力強く進展していくよう祈念いたします。令和2年7月28日、日本国内閣総理大臣、安倍晋三。核融合エネルギーの実用化を実現するまでは、息の長い研究開発が必要です。そのためには、全世界の GDP の約8割を占める世界7極が共同で取り組んでいるITER 計画の成功が必要不可欠です。今後のITERの運転開始に向け、より一層各局が力を合わせて取り組んでいくべきです。これからのITERの建設活動が無事に進捗していくこと、また今後の世界7極のITER計画における協力のさらなる進化を祈って、日本国政府からの挨拶とさせていただきます。
Thank you, Minister Hagiuda and Prime Minister Abe. Next, we turn to the Republic of Korea, where we will hear from President Moon Jae-in.
존경하는 마크롱 대통령님, 폰데어 라이엔 EU 집행위원장님, 국제 핵융합실험로 ITER의 베르나 비고 사무총장님, 그리고 회원국 정상과 대표 여러분, 반갑습니다. ITER는 라틴어로 길을 뜻합니다. 우리의 길은 지구의 다른 생명과 함께 공존하는 것입니다. 우리는 지구를 지켜내기 위해 미래 에너지라는 꿈을 꾸었고, 우리의 꿈은 세계가 함께 핵융합 인공태양을 만드는 사상 최대의 국제과학기술 프로젝트 ITER를 낳았습니다. 오늘은 국제 핵융합 실험로 ITER가 장치 조립을 시작하는 기쁜 날입니다. 코로나로 인해 기후환경 보호가 더욱 중요해지는 지금 ITER와 각국 사업단이 인류에게 희망을 주고 있습니다. 우리의 길을 향해 도전하는 전 세계 과학기술자가 있어 든든합니다. 여러분의 노력에 존경과 감사의 말씀을 드립니다. 인공태양은 꿈의 에너지입니다. 바닷물을 활용해 거의 무한정 생산이 가능하고 방사능 위험이나 온실가스 배출도 없는 청정 에너지입니다. 인류가 새로운 과학기술로 개척할 때 늘 그랬듯 ITER 역시 수많은 도전과 시행착오를 겪었습니다. 이를 극복하고 오늘 장치 조립 단계까지 올 수 있었던 것은 ITER를 중심으로 7개 회원국이 함께 지혜를 모았기 때문입니다. 전 세계가 연대하고 협력해 이뤄낸 자랑스러운 성과입니다. 한국의 연구진은 1억 도에 달하는 초고온 플라즈마를 8초간 유지하는 데 성공했습니다. 세계 최장 기록입니다. 초고온을 견뎌내는 진공 용기는 핵융합에 필수적입니다. 한국의 산업체들이 10여 년에 거쳐 이를 개발해냈고 곧 ITER 건설 현장에 도착할 예정입니다. 한국은 방역 물품을 나누며 K방역으로 전 세계와 연대와 협력을 실천했습니다. 이제 과학으로 세계와 함께하고 있어 매우 자랑스럽습니다. 핵심 품목을 만들어 우리의 길에 한 걸음 더 가까이 다가갈 수 있게 되어 한국 국민도 매우 기쁘게 생각하고 있습니다. ITER의 거대 부품들을 조립하는 단계에서 또 다른 도전이 기다리고 있을 것입니다. 코로나로 인한 영향도 경계하고 최소화해야 할 것입니다. 각국이 그동안 제작한 품목을 이제 하나로 완성하듯이 7개국이 하나된 협력으로 새로운 도전을 함께 극복할 것으로 확신합니다. 한국 역시 우수한 과학기술자들이 이트에 더 많이 참여할 수 있도록 지원할 것입니다. 2050년 청정하고 안전한 핵융합 에너지 실현을 위해 국제사회와 함께할 것입니다. 밤하늘의 별은 핵융합으로 빛납니다. 세계가 지혜를 모으면 인공태양이 인류의 미래를 밝게 비출 것입니다. 지구를 지키는 우리의 길을 응원합니다. 꿈을 현실로 만들어가는 여러분을 응원합니다. 감사합니다.
Thank you so much, President Moon. We are deeply honored by your presence and participation. We now turn to 𝗖𝗫 𝗪𝗶𝘁, the Director General of the State Atomic Energy Corporation, Rosatom, presenting on behalf of Vladimir Putin, the President of the Russian Federation.
Уважаемые дамы и господа, дорогие коллеги, друзья, позвольте огласить приветствие президента Российской Федерации участникам мероприятия по случаю начала сборки и монтажа оборудования установки ИТЕР. Уважаемые дамы и господа, приветствую вас по случаю начала работы по сборке и монтажу оборудования установки международного экспериментального термоядерного реактора ИТЕР. ИТЕР, ставший крупнейшим международным научно-техническим проектом, представляет собой яркий пример эффективного и взаимовыгодного многостороннего сотрудничества. Как известно, Россия является одной из стран-основательниц данной инициативы, призванной внести важный вклад в обеспечение энергетической безопасности человечества и играет активную роль в ее воплощении в жизнь. В основе проекта ИТЕР лежит разработанная в нашей стране концепция установки Tokamak. Сегодня ИТЕР вступает в решающий этап своей реализации. Несмотря на ограничения, связанные с пандемией коронавирусной инфекции, удалось сохранить бесперебойные темпы работ. Это позволяет рассчитывать, что цели проекта будут достигнуты в намеченные сроки, и уже в обозримой перспективе мы получим уникальный по своей мощности и безопасности источник энергии, эксплуатация которого, несомненно, будет способствовать решению задач устойчивого экономического развития и повышения качества жизни миллионов людей. Хотел бы искренне поблагодарить всех, кто на протяжении многих лет трудится над проектом ИТЕР. Особая признательность президенту Франции Эммануэлю Макрону, как лидеру страны-хозяйки проекта, представляющей площадку для реактора и оказывающей неоценимую помощь в его сооружении. От души желаю вам новых успехов и всего самого доброго. Президент Российской Федерации Владимир Путин. Уважаемые коллеги, позвольте мне также от себя лично поздравить всех участников проекта ИТЕР с началом нового этапа, сборкой и монтажом Токамака, который, по сути, является сердцем всего проекта. Это важнейшие события для всего термоядерного сообщества, ну и, конечно, для всей мировой науки. Важно, что, несмотря на ограничения, вызванные эпидемией коронавируса, работы по сборке, по монтажу начинаются в соответствии с графиком. С искренним, глубоким уважением отмечу усилия персонала центральной команды, домашних агентств и лично генерального директора организации ИТЕР господина Бернара Биго. Они сделали все, чтобы многочисленные участники проекта действовали как единая команда. Теперь главная задача для нас всех – обеспечить своевременный монтаж и сборку установки и получить первую плазму к концу 2025 года. Это позволит на деле продемонстрировать согласованность действий всех участников проекта и итоговую эффективность нашего международного сотрудничества. Россия выполняет все обязательства в проекте ИТЕР по внесению натурального и финансового взноса в полном объеме в строгом соответствии с графиком. В том, что сборка реактора началась вовремя, есть большая заслуга России. Верхние патрубки и шинопроводы были своевременно изготовлены и поставлены на площадку ИТЕР. Особо отмечу широту географии работ по ИТЕР в России. В Санкт-Петербурге идут работы по сборке катушки полоидального поля. В Нижнем Новгороде изготовлены и испытаны первые 4 гиротрона. В Москве, Санкт-Петербурге, Казани, Подольске и Новосибирске ведется разработка и изготовление 7 диагностических комплексов, необходимых для обеспечения полномасштабных исследований на стадии первой плазмы и, конечно, в будущих экспериментах. Большинство систем ИТЕР изготавливаются и интегрируются сразу несколькими партнерами из разных стран. Это требует полной слаженности в работе и согласованности действий. Убежден, что на нынешней стадии проекта своевременное выполнение каждым из партнеров своих обязательств по внесению как натурального, так и финансового взноса абсолютно необходимо для нашего общего успеха. Дорогие друзья, проект ИТЕР – это яркий пример открытой научной и технологической кооперации. Поэтому вслед за президентом тоже особо отмечу вклад в проект ИТЕР Франции как страны-хозяйки. Ей удалось создать уникальный климат для совместного эффективного творчества ученых и инженеров, рабочих и специалистов из разных стран. Дух ИТЕР воодушевляет нас всех, кто хоть раз побывал на площадке. Уверен, что нам удастся сохранить его на долгие-долгие годы. Дорогие друзья, уважаемые коллеги, я желаю нам всем дальнейшей успешной работы и удачи. И, конечно, желаю всем здоровья, здоровья и еще раз здоровья.
Thank you, Director General Tkachев, and in particular, President Putin. Now for the last stop on our global tour, we will turn to the Secretary of Energy of the United States of America, Dan Brouillette.
Thank you. It's a pleasure and honor to join you for such an important event taking place during extraordinary times. This year has been full of challenges for all of us, so I appreciate the opportunity to be with you in celebrating this significant milestone for the ITER project and the future of energy. The start of machine assembly means that site preparations have concluded and that the project is now receiving components from ITER members around the world. As a consequence, we can now begin to look forward to first plasma and the future beyond. As the United States Secretary of Energy, I'm responsible for the stewardship of 17 national laboratories, which are each spearheading basic and applied research projects in areas ranging from clean energy to materials science to exascale and quantum computing. Projects with incredible impact and world-changing potential. I'm also responsible for our nation's fusion energy efforts, which hold the promise of providing an economical, nearly unlimited, and clean form of energy for future generations. ITER plans to create, hold, and control the hottest material on Earth within some of the coldest materials, and to use that heat to generate electricity. It's an incredible engineering achievement to consider, and first-of-a-kind components that will make up the ITER machine are being fabricated to exacting tolerances around the world and shipped to the assembly, for assembly at the site. This new stage has been made possible through decades of collaborative research in engineering and fusion and plasma physics at government laboratories, universities, and companies all around the world. It's a profound story of human endeavor, and the best is yet to come. I'm proud of the significant work at our national laboratories to support this effort, including projects at Oak Ridge, Princeton, and Savannah River. And I'm equally proud of the participation of many U.S. companies. To cite just one example, a company from California is preparing to ship the first of 7 massive superconducting magnets that will comprise the ITER central solenoid. The production of these magnets is the result of close collaboration amongst the United States, Japan, and the ITER organization, and many other components are being fabricated at U.S. companies and laboratories for eventual delivery and incorporation into the reactor. The ITER effort has also helped to renew enthusiasm and optimism about the commercial promise of fusion energy. Several startup companies across North America have been established in recent years to explore potential new concepts for fusion energy, and we've engaged with a number of them in the hope of accelerating progress and reducing costs toward commercial applications. In closing, I'd like to recognize the hard work and the dedication of thousands of ITER staff and contractors at the site, and the many thousands more among the ITER members engaged in fulfilling the promise of fusion energy. While many are responsible for the conception, design, and progress on the project so far, all of the participating nations owe a special debt of gratitude to Director General 𝗪𝗁 for his dedication and expert stewardship of the project over the past 5 years. We in the United States are hopeful about a bright future for fusion energy, and we look forward to the assembly of the reactor and to the promise of what we will learn soon from the testing after first plasma. Good luck to the team in this critical next step of assembly. Thank you again. Let's go to work. Let's change the world.
Thank you, Secretary 𝗪𝗓. This brings to a conclusion our global tour. I would ask that all of you would perhaps welcome again back to the podium to conclude our ceremony, Director General Bernard Bigot.
Thanks again, Levan. It has been very rewarding to listen to this declaration by all the 7 ITER members. On behalf of all the ITER community, I would like to express our deepest and most sincere gratitude for this wonderful statement of support from the head of state, ministers, and other officials today, representing all the 7 ITER members. This support from the highest level of ITER members' government is inspiring. To know that we are all working towards the same goal for a future powered by fusion energy will be a constant source of encouragement as we go forward into machine assembly at ITER. I would like to conclude our celebration today by recognizing as well the essential nature of another commitment. I am speaking of the global ITER workforce. As in any other large human enterprise, nothing is possible without highly skilled and motivated staff who execute the work on scope, quality, and schedule. The ITER people are the best asset for ITER's success. Could I ask 3 people to join me on the stage? Laura Bertolo from Europe, the lead contract engineers in the assembling hall. Ashok Sharma from India, Tokamak instrumentation engineers. And Li Zhuang from China, an engineer working on Tokamak assembly. Thank you very much for joining me. Here in Provence and around the world, more than 10,000 people like them are working together to make ITER a reality. We could not do it without each of you. Those who design and manufacture the component, those who transport them over land and sea to the ITER site, those who install each piece with precision in its proper place, those in support role in finance and legal work, and those who prepare the operation. Unfortunately, we cannot have all of you with us today in person, so I have asked the 3 of you to join me on this stage to represent all the workers on our global One ITER team to say how grateful we are for your hard work, dedication, and professional excellence. I have with me a special crafted disc, this one. This disc is a little bit special. It is made of synthetic sapphire. We refer it as a nanoform disc because it can be inscribed with thousands of pages of material at nanoscale, which can be viewed with a microscope, and it will be last for thousands of years, fully preserved, whatever adverse condition it may face. As a small token of your gratitude to the ITER workforce, and to commemorate our celebration today, we will inscribe your name and photos of such a disc, plus a transcript of the statement given today in our many ITER language with additional photographic image. This disc will be attached to the ITER Tokamak building to serve as an enduring record for those who will retrieve it when ITER has achieved its purpose and completed its mission, and possibly to be transferred to the first fusion power plant in the world to deliver electricity on the grid. Thank you very much for your contribution, and so we will provide this inscription. But before leaving, I would like to offer you, each of them, this piece of the superconducting material, the one which will be on the Tokamak building with the magnetic coils. Thank you so much. As we conclude our ceremony, we leave you with a musical performance by the ITER Band. You may recognize the piece which we will find appropriate as we pursue the energy of the stars for peaceful purpose. These musicians are ITER scientists, engineers, and other staff. They come from many different backgrounds. For the past few months, during the pandemic, they have been largely isolated for each other. Yet, each one has contributed steadily, some teleworking, some on the ITER Worksite. Each one has recorded their individual track of music, which we have synchronized to make a single work of harmony. Like the 7 ITER members and ITER organization, we work together in the most integrated way, even if they are distributed all over the world. So thank you so much for all being with us today, and let's listen to the music.
1, 2, 3, 4.
Thanks a lot to all of you to have joined us during this celebration. And definitively, we are committed to assemble the Tokamak equipment and be successful as everybody expected. Thanks a lot.
Welcome to the third segment of our celebration today. First, we had a Worksite tour at 10 a.m. France time, and then we had the formal ceremony with the statements. We are now going to our press conference, and so I would like to give just a few explanations before those of you here or those of you joining us remotely will offer questions to Dr. Bigot. First of all, for those journalists who are joining us here, if you would like to speak directly to the microphone that is at the front, the only thing that we ask you is, because we respect COVID-19, please don't touch the microphone. If you just speak close to it, we will be able to hear you. So journalists who want to do that, you're welcome. In addition to the many journalists around the world that have been accredited to join us on our special platform for journalists, please send your questions whenever you like. And as many as we can, we will try to consolidate and to ask Dr. Bigot. Then in addition, if for some reason there are too many and we run longer than an hour, just send the questions in writing to any of the individuals who were named on the press release as contacts, and we will get back to you as soon as possible. First question, Dr. Bigot, is coming from Anita von Mont, and I should ask, for those of you coming to the microphone or submitting questions, if you can tell me the name of your news organization, that would also be helpful. So, first question, what is meant with the announcement that in December 2025, first plasma shall be launched? What plasma will this be? Is it only created with normal hydrogen atoms or already self-heating plasma able to produce more energy than the reactor consumes?
The first plasma in 2025 indeed will be just with standard hydrogen to check that all the different pieces of the Tokamak building, of the Tokamak installation has been properly assembled. It will not produce energy. It's just the first step to check that everything has been according to expectation. After that, we will install the system to collect the energy. Okay, as you know, the helium nuclei as well as the neutron will escape from the plasma and be collected by the wall, and we need to install this system. Furthermore, we will install also some extra heating in order to be able to reach a temperature of 150 million degrees. And last but not the least, we need to recycle the fuel, and so we will have what we call a tritium plant. So it's still a long journey to go, but it is needed in order to secure the performance of this very complex, first-of-a-kind installation.
Thank you. Next question, actually asked by a number of journalists, is, can you describe, from a practical standpoint, how you have managed to accomplish so much progress during the COVID-19 pandemic? And can you give any specific illustrations, either from ITER countries or from the ITER organization, where you experienced and dealt with particular challenges?
Indeed, we are lucky enough to have ITER members spread over all the planet. So when we experience the COVID-19 hitting China, and we feel that it could come to Europe and France, we have decided to anticipate the COVID-19 impact, and we set up an organization with most of the teleworking. We also impose to all the workers on the ITER site to wear masks. We were fortunate again that we received early enough before the pandemic some gift from China and Korea in order that we could provide the mask to a worker on the work site. And last but not the least, we rely on the high motivation of all the ITER members. Each of them were fully aware that it is quite easy to stop a project like this. You just order, stop, and everybody stop. But to restart, it would be a nightmare. So it's why we have decided to have what we call a continuity plan, preserving the critical activities we could not stop including to receive some of the components which were already loaded, shipped, and going on the sea. So it's what I call the ITER miracle. Okay, we have been fortunate enough to be able to go on continuing the activities without any infection within the ITER community.
Thank you. And can you give any specific examples about specific challenges, technical challenges otherwise, that arose during the last, say, 6 months?
Many challenges. I would say every day we have challenges. When you see the size, for example, of the cryostat base, the lower cylinder, the upper cylinder, they have to be manufactured with a very high precision, and they have to be leak-proof. And to be frank with you, for example, we have checked that it was so, and there was one part which was not complying with the specification. And so we have to grind it again and to redo it. It's a price to pay for high quality. So based on this experience, we have been able now to have perfect product to be installed. Once they will be installed in the Tokamak, we could not reduce them. We could not repair them. They have to be perfect before they come into the plasma, the Tokamak installation for plasma. I could speak also of some others. For example, with the coils, as I explained, we need to a precision which is below millimeter between the surface of the coils and the surface of the casing. And it was not easy to get it, and so we have to work very hard, and I am pleased that we comply with this specification also.
Thank you. Could you repeat which nations are involved in the assembly of the project, and how are scientists from nations who currently experience acute tensions, like the US and China, or China and India, how are they working together, and have diplomatic issues slowed the project or risk derailing it? Thank you.
The ITER project is based on an agreement. It has been decided that the 7 ITER members will procure in-kind the component. The responsibility of its assembling and installation is the ITER organization. But we need to rely on the experience of the staff, of the engineers, of the workers, which are manufacturers of these components. So it's why we work as an integrated team under the responsibility and leadership of the ITER organization for the assembly. And we are very pleased to work with many companies coming from all over the world, including, for example, China is responsible for the positioning of the cryostat, and many other countries are participating.
Thank you. There's a question from Alexander Teleshev, a special reporter with the TASS newswire in the Russian Federation. He says there's been a lot of progress technically with regard to plasma confinement, fuel injection, and other processes that directly control the efficiency of the thermonuclear reaction and can improve ITER success chances. Is there a cutoff for such proposals to be implemented? And if there is, how and when do you decide how the first plasma will be achieved?
As you know, this project is a research project. You never stop the research progress. The scientists are always very creative, imaginative, gaining experience, moving forward to a better understanding and control and mastering the physical phenomena. So from my point of view, the ITER project will go on, and in parallel, many progress will be done worldwide in many labs as well as other installations. The big difference is they have not the proper size in order to have what we call a burning plasma, a self-sustained plasma. And this is why we are ready to integrate all this progress in our project in such a way that we could demonstrate their pertinence in order to be able to provide fusion energy in the best condition when it will be ready to start.
Thank you. A question related to cost. what do you consider the cost in euros or dollars of the total ITER project? And are there also returns on investment in terms of economic benefit even before we receive full fusion power?
Clearly, this question of cost is a very often asked question. And it is very difficult to answer. Why? Because, as I explained a few minutes ago, a larger part of the construction is depending on the in-kind contribution of the several members. And everybody could understand that the workforce price in California is not exactly the same as in Mumbai. Okay, each country has its own economics capacity and procedures. So the only things I could do, I have a matrix. The matrix is the cost for the European Union. As you know, the cost for European Union is fully controlled by the European Parliament. And I know that the European Union is contributing 45% of the construction phase. And so it's quite easy, by comparison with the cost, if it would have been fully constructed and built and assembled in Europe, what would be the cost? And when we compare to the cost dedicated only to ITER, not speaking the, I would say, running cost of the fusion for energy and other project fusion of energy has in charge, the cost is of the order of 20 billion euro value 2015 when I came in.
Thank you. We see often in the news reports on big achievements by smaller projects, some things like Tokamak Energy or like the MIT project. How does ITER view those projects, and are they working together with you for the future of fusion?
I see all these smallest projects, as you name it, with a very positive attitude. From my point of view, it's already a success for ITER to have stimulated this new project in such a way, demonstrate that more and more people feel that hydrogen fusion could be a real option for the future. Second, as I have said, we have to decide, the design of this machine. We decided by 2007. We know we have to build it. We could not change the design every day. So we will go until the end with our design, integrating progress if it is possible, but some progress will not be. So it's good that other devices, much smaller, which from my point of view could not achieve the goal of ITER, which is a sustained plasma, a burning plasma, producing 10 times heat, the heat we are injecting in the plasma. I don't believe they could achieve that, but so they are complementary of our action, and we are very pleased to work with them as often as it is possible. We are not in a competition, we are really, from my point of view, complementary.
Thank you. A somewhat related question. Do you expect an actual fusion power plant to be a scaled-up ITER reactor, or is it some kind of hybrid that you would expect with other technologies that may emerge, such as spherical tokamaks?
Our plan is, once we have completed our mission to demonstrate the feasibility, viability, and economic competitiveness of hydrogen fusion, that we will replicate this type of devices, which looks the most promising, with a scaling up, maybe twice as large as this one, to be able to provide power to the grid. And but as you said, there is alternate devices, tokamak, spherical, as you said, for example, which could be good also. I don't want to eliminate any of them. Just let's have a fair competition and see what is the best, and maybe we could enrich each other.
Thank you. We see quite often by climate change experts statements that we need to go to 100% renewables. Also, that we need to move away from centralized production of energy and more toward decentralized. How do you view that idea?
You know, I am a physicist, I am a chemist indeed, and I trust, okay, the physical phenomena. When we are a population of nearly 8 billion, okay, soon 10 billion, with a very large urbanization, when we have highly concentrated means of production, you need continuity and massive production of power. And renewable energy, by the way, all come from the sun, okay, radiation, okay, on Earth, on the sun energy flux. They have two limitations. The largest limitation from my point of view is their, okay, diffuseness. Okay, you collect only a limited flux of energy by square meter, and we could not change that. Sun has been working this way for 5 billion of years and will go on 5 billion more. So it is an input data, flux of solar on Earth. And so if you want to power 10 billion of inhabitants, mainly living in cities, 80% of the world population is now living in cities. If we want to have large, okay, production means, continuity and massive production is needed. Whatever the progress on storage, I do believe that the order of energy we need, whatever the saving, will not work. I don't say that, okay, renewable energy has not to be considered. They have to be considered as much as we can. And very large project has been made indeed in the very few decades. But from my point of view, it is impossible to expect that we have 100% of your renewable energies. Okay, maybe just a small house, maybe, but not at the size of humankind. So it's why we need a complement source of energy which will fit and okay, adjust with the weak point of renewable energies, which is massive and continuity. And you could complement, which means that if you have a need, you could increase your power production. If you don't, it's a very nice solar day, as it is today in Provence. We have a lot of wind. Okay, you could shut down the fusion power and start it again immediately when the clouds will come in. So it's very good that we have these two complementary technologies.
Thank you. About 5 years ago, there was a lot of skepticism about the possibility of ITER succeeding. How did you turn the project around?
It's not myself we have turned the project around. It is the ITER members. You know, when I was requested to consider to take this responsibility, and indeed I was not at all prepared to do that, I say, sorry, I am not a miracle man, but just I know the recipe in order to be successful. And so if the ITER members agree to follow the rules I propose to them for the governance of the project, will mean first, clear decision process. I feel sorry to say, I have requested that the ITER Organization Director General is fully empowered to take decision. Clearly, it means to analyze the pros and cons of any decision, to consult, to have large discussion. But when comes the time for decision, please take decision. Second, we have 7 ITER members, 7 domestic agencies. Before, we were working more in parallel, in some silo. I say it could not work. We have to work in the most integrated way, as one ITER team. And last but not least, we have to be realistic. Okay, the schedule to deliver this project initially was much too enthusiastic. Okay, we come in, okay, I consult a lot of industry, I consult a lot of experts, and we come with a thorough review, and I present to the ITER members my conclusion. My conclusion was not enthusiastic for them. Before, it was felt that ITER first plasma will be 2020, and the full fusion power was 2025. And I explained it was physically impossible. They have to accept, and it was very challenging to have a schedule which will be first plasma by 2025 and full fusion power through what we call a stage approach with a sequence of complement installation of component and some experiment for the scientists by 2035. So I don't know if it will succeed. We work hard, and I am pleased to say since 2015 we are on track. We have been able to deliver according to our plan and our schedule with high quality. It is not my responsibility. It is the responsibility of the ITER members and all the staff. In my role, I am just, as I said, a facilitator. I don't prevent the other to work well.
Thank you. A question from Nate Gronewald at E&E News. After first plasma is achieved and experimented with in 2025, we see that it will be followed by a quote, shutdown phase. What is the purpose of that and the next steps?
First plasma, as I explained, the main component of the Tokamak, the vacuum vessel, leak-proof, huge, toroidal vessel, more than 1,500 cubic meter. The 18 vertical coils, what we call the toroidal coils, the 6 vertical ones, the central solenoid, all the cryogenic plants, all the different systems will be installed. And if it works, it will be a major landmark. But we know in order to complete our mission, we need some more equipment. We don't want to put this equipment immediately, because if, for example, we face a leak and we have to make some repair, we will have to disassemble what we have assembled, without any benefit. So the next step will be nearly during 2 years to install what we call the first wall, the panel which will collect the energy coming from the neutrons when they will be hit. And it's why, after this installation with robots, you have to understand that each of these parts is weighing more than 4.5 tons, and only the robots could install them, and there is 440 of these tiles. We will be able to offer to the scientists the possibility to start, with a plasma which will deliver some energy. But still, we will need some extra heating. And that's why, after 18 months, fully dedicated to the physics experiment, we will take over, the machine and, install the extra heating. And second, campaign of experiment will go before we finally install the recycling plants for the fuels.
Thank you. With the additional challenges from the coronavirus outbreak, will it be necessary to extend the ITER construction schedule and/or ask members for extra resources? This is from Dan Cleary at Science Magazine.
Clearly, the pandemic has impacted the schedule, initial schedule. You know that, for example, in some countries, for example, Italy, we have the workshop which has been stopped for nearly 2 months. Also, there is quite a large disruption in the supply chain, also limitation in the capacity of some of our expert engineers coming from a remote country to France. But I see an extraordinary motivation to try to recover this impact. I have been requested by the ITER Council to assess the impact of this COVID-19 shutdown, and by the end of September, I will report on this assessment, and I could say you more. You listen, come as me, by all the higher dignitaries of the ITER members. They are willing to have first plasma as soon as possible. So we will try our best in order to keep with our commitment. But again, we have to be modest and humble. If it is physically impossible, whatever the price we will pay, we will have to accept. It will be a delay, of a few months. I don't believe it will be a major step back, because maybe we could recover after that.
We have a question here. I don't have a name, but it is, I assume, from China. could you describe in particular the role of China as an ITER member, and how do you think China is doing as a partner?
China is a major partner. They joined the ITER project indeed, in 2003, as you know, and they learn very rapidly, on fusion. It's very impressive for me. They procure a lot of equipment. They are very reactive. So for me, just a very good example of the strong commitment of the ITER members. I am pleased to see that many of my Chinese colleagues demonstrate high skill and motivation, and so I wish that they stay as such up to the very end. So thanks to China, as I will say, thanks to all the 6 other members.
We have a historical question. Could you tell us how it was that ITER was chosen to be placed in Cadarache in France rather than somewhere else?
It's a difficult question, even if it is public. Indeed, fusion has always been something important for France. You have to remember that, for example, the jet has been under the leadership of French engineers, as well as the beginning of the ITER project, when it started in San Diego in the US, Naka in Japan, and Garching in Germany, in Europe. And so there were a strong motivation of the scientists to have ITER in Europe, and if possible, ITER nearby the CEA Center, Atomic Energy Commission, where you have a superconducting magnet, Tokamak, which was working since the 1980s. So the French scientists pushed for that. Second, France and Europe was considered by the 7 ITER members as a well-balanced position. All of them trust that France could be serious about nuclear safety, engineering capacity, welcoming of the different countries. And so it was a negotiation and discussion, and France has been chosen, and I am pleased and proud that this has been decided. And as you know, France is doing everything they can in order to accommodate. And last but not the least, and I guess my ITER colleague will say, Provence is not the worst place to be in the world to make science. I will not comment more, but I do believe that worldwide it is well known that Provence is a very pleasant place to be.
The last question that I have, unless we get more, is we understand that fusion power is primarily expected to produce electricity, and that electricity currently represents only 20% of global energy consumption. When you look toward the future, how do you see the rest of the 80% being made up, or can you use fusion for other applications?
As you see, fusion first produces heat, and so we could imagine that we will use the heat directly. Why not? It's happened in many countries where you have a network for heat transportation, and you could heat the cities and so. Second, I do believe that the electricity will take over many other energy consumption. Now, for example, you know, many cars are just running with gasoline. We see more and more cars running with electricity, with power. We do believe it is a future for transportation. I see very recently a plane with only electricity power. So from my point of view, if we want to have a clean energy world, environmentally respectful, we will use more and more electricity.
Thank you. That concludes, unless we have anyone here. I think many of you have interviews already lined up with Dr. Bigot this afternoon. for those of you who have not already interviewed. So this brings our entire press conference as well as the overall 3 phases of our Start of Assembly celebration to a close. Thank you to all of you here who have joined us. Thank you to all of you who have joined us from around the world. We invite you to continue to follow our progress as we work to make fusion energy the energy of the future. Thank you.
Thanks a lot. Thank you, 𝗪𝗶𝘁.